So, hello guys, we are first year students of EIT College from group number 1 of Division 3. We are here to present our topic of COE, that is Complete Instruction Execution with Exam. So, these are the group members of our group and myself, Parth. I'll give the total overview of our topic. So, let's begin. Overview. In computer science and engineering, instruction execution is the process by which computer executes the command in a program. Each instruction is a binary code that is loaded into the computer's memory and then decoded and executed by the processor. Instruction execution is a fundamental concept in a computer architecture, and understanding how instructions are executed is essential for developing efficient and effective software. To execute a complete instruction, we need to take help of some basic operation, and we need to execute this operation in some particular order. Then what are these operations? First one, fetch instruction. Second one, fetch first offer. Third one, perform addition. And the fourth one, load the result into the specific register. Let's understand by an example. Consider the instruction, that is add content of memory location R2 to the content of register R and store the result in register R. For simplicity, assume that the address of R2 is given explicitly in the address field of the instruction, that is, in the instruction direct addressing mode is used. These are the main steps of execution of instruction. First, fetch instruction. In this, the processor fetches the instruction from memory. Second, decode instruction. In this, the processor decodes the instruction to determine what operation it needs to perform. Third one, read address from memory. After fetching the contents of register, the processor adds the content of two registers into the specific register. And the fourth one, execute the instruction. In this, the processor writes the result of the operation back to the specific register. So, these are the 8 steps are required to implement the above operation for the single bus. For continue, I would like to call Arif.
Let us understand steps to be followed. Step 1. The instruction fetch operation is initiated by loading the contents of the PC into the MAR and sending a read request to memory. To perform this task, first of all the contents of PC have to be brought to internal bus and then it is loaded to MAR. To perform this task, control circuit has to generate the PC signal and MAR signal. After issuing the read signal, CPU has to wait for some time to get the MFC signal. During that time, PC is updated by 1 through the use of the ALU. This is accomplished by setting one of the inputs to the ALU to 0 and the other input is available in bus, which is current value of PC. At the same time, the carry in to the ALU is set to 1 and an add operation is specified. After issuing the read signal, CPU has to wait for some time to get the MFC signal. During that time, PC is updated by 1 through the use of the ALU. This is accomplished by setting one of the inputs to the ALU to 0 and the other input is available in bus, which is current value of PC. At the same time, the carry in to the ALU is set to 1 and an add operation is specified. We can understand it by the given diagram.
Okay, so the next step is step 2. Let us learn about the different terminologies used in this step. The term step Z typically refers to a particular point in a computer's instruction cycle where the processor signals to memory that it is ready to receive the next instruction. The PCN refers to the process of loading the program counter with the address of the next instruction to be executed. Wait for MFC refers to the fact that the processor may need to wait for a memory fetch cycle MFC before it can execute the next instruction. So in this step, the phrase step Z out PC in wait for MFC required for execution of instruction describes the process of the processor completing the Z step loading the program counter with the address of the next instruction, and then waiting for a memory fetch cycle to complete before it can execute the instruction. This process is all done on a single bus, which is the pathway that the processor uses to communicate with memory. Okay, so step 3, the MDR out IRN step is a crucial step. Is a crucial part of the instruction cycle for single bus computer architectures, as it allows the processor to retrieve and execute instructions stored in memory. What is MDR? The MDR is a register in the processor that holds the data that has been retrieved from memory, and the IR is a register that holds the instruction that the processor is about to execute. In step 3, when the processor is ready to execute an instruction, it first loads the address of the instruction from the program counter into the memory address register. The processor then signals the memory to fetch the instruction located at the address stored in the MAR, which causes the instruction to be loaded into the MDR. Once the instruction is in the MDR, the processor can move it into the IR register, which is the next step in the instruction cycle. The IR holds the opcode of the instruction, which tells the processor what operation to perform as well as any operands or parameters that are needed for the instruction. Once the instruction is in the IR, the processor can decode the instruction and execute it, which may involve moving data between other registers and memory locations, performing the arithmetic or logical operations, or branching to another instruction. Okay, so the step 4, that is the address field of IR out MAR in read step, is a crucial step of the instruction cycle in a single bus computer architecture, as it allows the processor to retrieve the data from memory that is needed for the execution of the current instruction. In this step, the first step is in this process is to extract the address field from the IR and transfer it to the memory address register, that is the MAR. The MAR is a register processor that holds a memory address of the location that the processor wants to read from or write to. Once the address is loaded into the MAR, the processor signals to the memory to read the data stored at the memory address. This is done using a read signal, which tells the memory that the processor wants to read data from that location. So the next step is that the memory then retrieves the data from that memory location and puts it into the MDR, which holds the data that has been read or written to memory. The data that is read from memory may be an operand or parameter needed for the execution of the current instruction. Let us take an example. If the instruction is a load instruction, the data read from memory would be the value that needs to be loaded into a register or memory location.
Step 5. The destination field of IR, which contains the address of the register R1, is used to transfer the contents of registers R1 and register Y and wait for memory function to complete. The instruction may require waiting for the memory function to complete before proceeding with the next step. It suggests that the instruction involves reading or writing data to memory, which can be slow operation compared to operations that only involve registers or caches. When the read operation is completed, the memory operand is available in MDR, that is memory data register. This suggests that the CPU may have a specific register or buffer where it temporarily stores the data that is read from or written to memory. This can help improve performance by allowing the CPU to continue processing instructions while the memory operation is being performed in the background. Step 6. The instruction likely involves performing an addition operation using one or more operands, which may be stored in registers or memory locations. The addition operation may be performed using a specific CPU instruction or a sequence of instructions that implement the required logic using the CPU's ALU, that is arithmetic logic unit, and the result of the addition operation may be stored in a specific register or memory location depending on the instruction and its operands.
Okay, so now that we have learned about complete instruction execution, we are going to look at an example of it. So here's an example of how to execute the instruction add R1 R2. So R1 R2 are two registers, and we are going to initialize R1 by 7 and R2 by 5. So the first step here is fetching. The instruction add R1 R2 is fetched from the memory into the instruction register, that is IR. And then comes decoding. The control unit of the CPU decodes the instruction to determine what operation is to perform and which operands are involved. Then comes reading. The CPU reads the contents of R1 and R2 from the register file and loads them into the ALU. So R1 will be loaded as a first operand and R2 will be loaded as a second operand. Then the further step is execution. The ALU performs the addition operation on the two operands and proceeds and produces the result. The ALU adds 7 and 5 together and gives us the result 12. Then comes the writing. The result of the addition operation 12 is written or is written back or stored to the destination register R1 in the register file. The contents of R1 are updated to 12. So after the execution of the instruction R1 R2, the contents of R1 will be updated from 7 to 14. I hope you guys have found this video helpful. Do make sure to like and share with your friends. Thank you.
Hello everyone. The step number 7. This is instruction is not a typical machine instruction and its behavior depends on the specific system and context in which it is used. In general, the instruction seems to suggest that the constant of the register R1 should be returned to some output device or port Z out and then read back into the register R1 is in. Here are the steps involved in executes this instruction. Write the context of a regular R1 are returned to an output device or port Z out. Read the contents of the output device or port Z out are read back into register R1. So next example, let's say that the value of register R1 in is 50 has a result of executing the add R1 R2 instruction from the previous example. Here how the instruction would be executed. First write the context of register R1 50 are the write to the output device or port Z out. Read the context of the output device or port Z out are read back into register R1 overwrite the previous value of 50. So the next step number 8. This is instruction is a special instruction that signals the ends of the program when the CPU encounters the end instruction. It stops executing instructions and help the program. Examples: assume that the add R1 R2 instruction was the only instruction in the program. Execute it to the result in register R1 begin updated to 50 when the end instruction is encountered. The CPU will stop in executing the instruction and halt the program. In this example, the program simply adds the value in the registers say R1 and R2 and stores the result in R1. Then halts if there were more instructions in the program, they would be executed in a sequence unit. The ends instruction was encountered at which point the program would halt.